Okay, welcome back. So we are slowly facing the end of the course. Unfortunately, this year, due to this remote distance way of doing teaching, I will probably not be able to cover all the material that I did cover last year. So for instance, I don't think we're going to be able to deal with basic concept of chemistry such as hybridization of orbitals and stuff. But nevertheless, I think we'll be able at least to define some fundamental concepts that will be needed in the final exercise you will be doing on quantum chemistry calculation. So today we really go into the territory of quantum chemistry. So what is quantum chemistry? Is basically a branch of theoretical chemistry or physics. I don't see a big distinction there between chemistry and physics, in which you derive the basic properties of molecules in terms of their structural and their reactions and their binding, directly bottom up from the quantum mechanical theory we've been discussing over this course. So from the point of view of quantum mechanics, well, first of all, let's start from the scratch. We know molecules are bound states of atomic nuclei and electrons. So from the point of view of quantum mechanics, we have a bunch of degrees of freedom, which I draw as nuclei with different colors, and different colors may correspond to different charges. So for instance, say this is the nucleus of type A, this is a nucleus of type B, and this is a nucleus of type C. And maybe A is an hydrogen, B is a carbon, and C is an oxygen. And these are the atomic nuclei that I draw as little circles, although their size is so small that I wouldn't be able to draw it here, because it's about 100,000 times smaller than the typical size of an atom, and say maybe one order of magnitude, or maybe another factor 3, 4, when you go from atom to molecule. And around this, there is a bunch of electrons that I would draw as a cloud that can sort of, populate with their wave function the system. And it is a molecule as long as the energy of all these particles being stuck together is smaller than the energy of their constituents to be alone, flying for their own fate around space, or some subpart of the constituents to be alone. For instance, when you say that H2O is a molecule, or let's take the simple system, H2 is a molecule, a simple possible molecule. Well, that means that it is more convenient energetically. I have, 2 protons, and I have, let me draw in yellow the electrons, actually. And I have a cloud of electron here and a cloud of electron there. And these 2 hydrogen atoms, like this, this is what would be H and H. So they form a molecule when it's convenient energetically for them to go into configurations in which they stick together. The wave function is stuck together. Okay? And it would be nice if we could derive all the basic properties of small and large molecules, including proteins, membranes, lipid acids, directly from quantum mechanical principles, because then we will have had drawn a line connecting, say, life through their fundamental phenomenology, through down molecular biology connects biology to molecules, and then Quantum chemistry connects molecules down to the very essence of fundamental aspects of physics. So this is what I call a first sketch of the grandest unification, life with fundamental physics. That would be fantastic, right? And that's a little bit what we are trying to do in this last part of the course, or at least we're trying to look at, gaze at. We will not be able to go too much into it. But from the point of view of quantum mechanics, what does it mean to solve quantum chemistry? Well, to solve for quantum chemistry basically is to solve for the following Schrodinger problem. I have a Hamiltonian, and this Hamiltonian consists of a number of electrons, which I will label with an index I, and they will have their momentum, and of course, all the electrons have the same mass. That's the kinetic energy for the electron. Let me call small m the mass of the electron. There will be a sum over the atomic nuclei, and I will call that as alpha, the label that we alpha. And of course, each atomic nucleus will have a different mass. And then, of course, there will be a potential U. And the potential will depend on the collection of all the electronic coordinates, which I will collectively recall as R, and all of the nuclear coordinates, which I collectively denote as Q. So R will be the position of the first electron throughout the nth electron. And Q will denote the collection of the first nucleus throughout the last nucleus. So this is the number of atoms, if you want, that form the molecule. Now, clearly, I'm not resolving the internal motion of the atomic nucleus because that's, in fact, called nuclear physics. And nuclear physics occurs at an energy scale of MeVs, mega electron volts. And as we shall see, this is far away from the physics that we're interested in here. Or if you want, conversely, you can talk about lengths. Nuclear physics occurs in 10 to the minus 15 meters length distance, and we're interested in physics in 10 to the minus 10, 10 to the minus 9. So we don't have to worry about nuclear physics. Now, how does this potential look for? Well, we know that basically chemistry is completely driven by electrostatics. So let me write this potential, spelling out all of its parts. First of all, we have an interaction between electrons, and this is, of course, repulsive. Because they have the same charge. So there's a plus sign on top of this potential. And now I have a sum over I not equal to J. We don't count the interaction of an electron with itself, which would give an infinite energy. This is one of the subtleties of physics, but I'm not going to that. Why I had to have to count the energy of everything with everything else except with itself. You know, this is one of the delicate points in physics, but never mind. Now, I want to make sure I don't double count the interaction, because if I write this expression as is now, I have, say, suppose I have three particles, 3 electrons, just for an example. I would have the interaction 1, 2, 1, 3, 2, 3, because I'm summing over J, I'm summing over all A's and all J's with I not equal to J. So I can be 1, 2, or 3, and J can be 1, 2, or 3. So that means that in general, I have quite a few terms. You see? But some of these terms are actually double counted because the interaction between electron 1 and electron 2 and the interaction energy between electron 2 and electron 1 really is the same interaction energy, and I shouldn't be counted twice. So I have to divide by 2 this sum to avoid double counting. Okay? That's because electrons are identical, and the interaction between a pair of electrons is symmetric. The Coulomb interaction only knows about the distance, and so for all the symmetries of the problem, have a redundancy in counting. So that's the Coulomb repulsion. On top of the Coulomb repulsion, I also have the Coulomb repulsion between the atomic nuclei, because they also have charge, which is positive, and therefore positive charges repel each other. So let me say I have 1/2 sum over alpha not equal to beta, but now alpha goes from 1 to the number of atoms. And this time I have the repulsion, but I also have the atomic number, which tells me how much charge there is in each of the atoms. Okay, of course, if my interaction were only this Coulombic repulsion, then clearly the system would boom away because of Coulombic repulsion. There would be no chance to having any stable matter. As a matter of fact, we exist because there is attraction between electrons and nuclei. So now I'm going to write the following. And I want to emphasize that this extra term is the only attractive term. There is a Z alpha because one of the nuclei has a charge Z alpha, ZE, while the electron has a charge E. The summation does have the 1/2 because these are distinguishable particles. So electron 3 and nucleus 1 is not the same as the nucleus 3 and electron 1. So you see why the degeneracy of the particle species is actually responsible for the 1/2 factor in front. And finally, there's a negative sign because I have an attraction. Very well. So what we really want to do is to solve the Schrodinger equation for this system. And so in general, my wave function psi, the ground state, suppose we're interested in the ground state, will depend on the electronic and nuclear coordinates. So how does the Schrodinger equation look like? So if I go back here, let me call this term here, notation-wise, T electron, or let me call it TR. Why? Because it will contain spatial derivatives or Laplacian with respect to the electron coordinates that I denoted with R. And I will call this TQ because the kinetic energy of the nuclei, of the nucleus, will contain partial derivatives with respect to the nuclear coordinates, which I denoted with Q. So if I were to write my Schrodinger equation, this would be TR plus TQ plus my potential of R and Q applied to my wave function of R and Q equals to E psi of R and Q. That's my Schrodinger problem, right? I mean, I've made no approximation whatsoever so far, other than neglecting relativistic effects and therefore magnetic effects in the Schrodinger equation. So that's the full glory problem. And this is too complicated, too complex. But you see, we don't really need to solve the problem in all this full glory. And that's where physics intuition or chemistry intuition or physical chemistry intuition, depending on how you want to think about it, comes into play. Why? Well, I think one of my mentors, who's now passed, he was very old, and he's one of the most influential scientists I've met, and really shaped my education in my early stage when I was a PhD student, and I owe him perhaps 99.9 of the, well, probably not 99.9, maybe the other a little bit is also to my PhD advisor, but many of the sort of drive and go into science. He's Jerry Brown, Professor Jerry Brown from Stony Brook. He was a fantastic nuclear physicist who invented countless, he contributed in a countless way to the progress of understanding nuclear force, among other things. And he always told me, don't think about physics as the science of making complicated calculations that can impress people. Physics is the art of making the right approximation. Because if you can make the right approximation, a complex problem becomes simple and you grasp the bulk of it and you take home insight into nature. So what is the right approximation here? The right approximation in this problem was invented in the early part of the last centuries, and it's called the Born-Oppenheimer approximation. Now, in case you're wondering, Mr. Oppenheimer is in fact the same guy who led the Manhattan Project leading to the construction of the first atomic bomb. Those were the years where the scientists could not withdraw from having to be involved in something as dramatic and as horrifying for a certain point of view as building an atomic bomb. And I hope you have heard this story. Again, I don't have the time here to tell you all about it, but if you go and read books, you'll discover that all the stories of the Manhattan Project was starting from the fact that Einstein at some point realized that his own equations for special relativity were allowing for the conversion between binding energy of nuclei into kinetic energy of broken up nuclei, so converting nuclei into thermal heat, essentially. And that certain elements were allowing to have a favorable, if you were able to break certain elements, you would have had gain of energy. And he sort of imagined what elements could they be, and they realized they were basically heavy nuclei such as uranium. And then he discovered that the Germans had all the uranium mines, and basically had most of the uranium in the world was in Africa, held by the German colonies. And so, since many of the brilliant scientists of the early part of the 20th century were from the German side, including Mr. Heisenberg, he knew that they would have gotten to the same conclusion very close. And if Hitler would have an atomic bomb, who knows what would have happened to World War II and to humanity in general. So he wrote a letter to the United States president asking for the setting of a project to build a bomb, even though Einstein himself was a pacifist in many respects, or at least that's what I heard. So that's how the whole project started. But let's not get sidetracked too much. Oppenheimer was a fantastic scientist, and he was the inventor of this approximation. So let me tell you a little bit about it. What is the idea? The idea is that nuclei are heavy compared to electrons. Now, physics starts when you can find two things that are not similar. When you can find a gap between scales. When you can build a dimensional parameters divided into physical quantities, which is either much greater than one or much smaller than one, depending how you arrange them. And once you find that, that's your hint to build an approximation. And in this case, The parameter is the mass of the electron compared to any mass of the nucleus. Well, in the lightest, most unfavorable case, this is, roughly speaking, 1 over 2,000. That's for the hydrogen. But for heavier nuclei, this is at least 1 order of magnitude larger. Therefore, really is something different. Now, what happens when two objects have a different mass? Well, think about a cow. I'm going to draw a cow, starting from the horn. Okay, that's as much as I can go. Here are the tits, here are the legs. It's a very bad cow. I don't know how much exactly does a cow weigh, but I would say it will weigh somehow 400 kilos. That would be my best guess. Maybe even more. A big fat cow, maybe something more. And if you've ever been around cows in the countryside, it's full of mosquitoes. I don't know how much a mosquito weighs, but my best guess is it's going to be around 1 gram or even less. So 10 to the minus 3 kilograms. Now, in this case, the ratio between the is actually 10. It's 4 in 10 to the 2 divided by 10 to the minus 3. It's 10 to the 5. So it's even 1 order of magnitude more than, say, carbon atom with respect to electron. But it's not particularly important. The important thing is there's a really big separation of mass. So if you look at cow from afar, you will know that the mosquitoes are flying extremely fast around the cow. And by the time the cow moves by 1 step, the mosquito have gone all over the place many, 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 many times. So if you sit on top of a mosquito and look at the world, you will be basically, if you look at the world with the eyes of a mosquito flying around a cow, you will be basically seeing a static cow still in front of you, and you will be continuously surfing the surface of the cow, looking for a good spot to eat whatever is on its body or remains, whatever. You got the point. But the cow is not really a static guy. The cow moves around at a much slower pace, looking for grass. So you can either solve this problem as a complex problem, closing your eyes to all the differences there are in the system, or you may say, I can simplify the problem, and I can say, I consider that for the time scales that is relevant for the mosquito's dynamics, the cow is static. And anytime I move the cow, I have to solve a different problem in which mosquitoes fly around a static cow. So I can split the problem as a sequence of simpler problems where a cow is in different position. And if all I'm interested in is where are the flies around the cow, I can look, instead of having one big problem, cow and mosquito moving together, I can split into many simpler problems in which the cow is in different frames, and in each frame I have a cloud of mosquitoes flying around, which I can compute. So this is the idea of the Born-Oppenheimer approximation, with the idea that the cow is the atomic nuclei, and the mosquitoes are, of course, the electrons. So we want to decouple the motion of the electrons from the motion of the nucleus. And in practice, this is done by taking the wave function and do exactly what we did with the decoupling of orbital and radial angular momentum and radial motion. And we say that a way to implement this idea of decoupling is saying that basically my wave function decouples into a wave function for the nucleus and a wave function for the electrons, which will depend parametrically on the nucleus. I'm going to explain in a moment what I mean by parametrically. But basically, it's like saying, if I put my carbon here, my hydrogen here and my oxygen here, and I keep them fixed, I solve for the Schrodinger equation in the field of these three fixed nuclei. Of course, the solution will depend on where I nailed these three atoms and their coordinates. But these will basically enter as a variable parameters I can adjust, but these are not supposed to have any dynamics. They're just nailed down there with a hammer. Okay? So that's the idea of parametric dependence. So, but from a mathematical point of view, all I'm doing is postulating the structure and plugging in into the Schrodinger equation. Now, if you do that, you go back on this equation that we wrote somewhere above here. Well, let me write it again. dr plus tq plus vrq. And now I'm going to write chi phi is equal to E chi phi using these ansatz. And if you now remember that this chi only depends on R, on Q, and phi depends on both R and Q, then you'll discover that some of these terms we can go through. For instance, TR can go through here because chi doesn't depend on R, right? So you get the following equation. Chi of Q, dr of phi of R and Q, plus TQ phi of R and Q times chi Q plus U of R and Q chi of R and Q equals E chi phi. Okay, now comes the major simplification. The major simplification comes basically in neglecting the kinetic energy of the nuclear motion in some of these derivatives. Okay, let's see how. So what we need to do is to do some trivial mathematical manipulation first. So I'm going to just write it down for you, and you can, do it yourself. There's a part here, you see, this part. Let's look at it for a moment. Well, this is chi tq phi plus phi tq chi negative some cross product, which I'll write this way. I'm going to spell it over explicitly. This part I left implicit, the first two terms, and the third part I'm going to give an explicit expression because this is going to be the gradient of chi alpha, gradient of phi alpha. Okay? Well, this is just mathematical manipulation, nothing particularly difficult, just rules for differentiation. So, in the end of the day, we've come to the following equation just by manipulating the Schrodinger equation and assuming the factorization of the wave function into chi and phi. So at the moment, there is no approximation yet. And let me write down the Schrodinger equation for this system. Just, this is just a result of applying the rules of differentiation, basically, to a product of function. And there is no particular approximation done so far. Let me group the terms in the following form. I want to just say one time more, what I've done was just take the Schrodinger equation and plug it into a wave function in the form of chi times I, and follow up with doing the differentiations. So you can do it yourself, and you will come to the very same conclusion. So this is the moment where we do make an approximation. And the approximation we're going to say is, anytime we have a derivative with respect to the nuclear position of the electronic wave function, we will assume that this is small. Why is that? Well, basically, because these will come with a ratio of the mass of the heavy nuclei, and basically this is corresponding to say that the motion of the nuclei is slow compared to the dynamics of the electron. Let me say it again. This is the wave function of the electrons when nuclei are in position Q. And the derivative with respect to Q is proportional to the momentum of the nuclei. So by neglecting all the terms in this form, we are neglecting the motion of the nuclei when we are interested in the cloud of the electron around the nuclei. We are neglecting the motion of the cow when interested in finding the distribution of mosquitoes around the cloud. So this particular feature here is called the adiabatic approximation. And if you do that, and if you assume the adiabatic approximation, then you're basically neglecting this term here. And you have a much simpler Schrodinger equation. So let me divide by chi the Schrodinger equation. So I get a chi here. This goes away. This goes away. And this goes away. So, and this is of course equal to 0. So we have obtained a simpler Schrodinger equation by taking the cow-mosquito ratio approximation, the so-called adiabatic approximation. Now we take the fundamental step, is that we solve the problem in 2 steps. First, solve the electronic problem. And the electronic problem consists in solving the Schrodinger equation for the electrons. Keeping the nuclear fixed. Now clearly, well, let me write it this way. This is the Schrodinger equation for the electron. So physically, what does this equation mean? I'm taking the nuclear at fixed positions Q, and I'm solving a Schrodinger equation for the electrons, in which I leave the nuclear fixed. Now, clearly, the solutions of this equation will depend on the electronic coordinates. The wave function will give me the distribution of electrons, but will depend parametrically on the nuclear positions. And the energy will depend parametrically on the nuclear position, because if I change the nuclei, the cloud of the electron, the energy will change. So after I've done that, and this is only the ground state, I'm assuming The particle, I'm not interested in the excited state. I'm assuming the electrons immediately collapse to the ground state because their dynamics is very fast. They dissipate their energy, go down to the ground state very quickly. Then after I solve this problem, I will get an energy that will depend on the Q. So I can go back on this equation and plug in back. And the result will be a second Schrodinger equation. This time, where this energy will play the role of a potential energy for the nuclei. Okay, it sounds completely confusing. But let me stop for a moment and summarize physics-based what we've done. We have a system made of electrons and nuclei. Electrons are light, nucleus are heavy. Whatever happens with electron, it happens on a much faster timescales than whatever happens with nuclei. Not only electron move fast, whatever moving means for quantum mechanics, but also if you have an excitations for the electron, it will relax back, emitting energy, dissipating energy much faster. How do we know? Well, look here. This is a small, this is a heavy object. It takes about 1 second, maybe 5 seconds, to lose its kinetic energy on the ground. If I take a bunch of coins, you see that the dissipation, in proper suitable physical condition, has a characterization for dissipation timescales that is much faster. So the electron basically fall on the ground state instantaneously compared to the time where the nuclei move. So what we have done in this complicated mathematical formalism is simply implementing the following idea. For all practical purposes, I can always think that first look at the system of nuclei made by static nuclei and compute the ground state energy of the electrons around this static nuclear configuration. This is the essential information. This is what is called the electronic problem of quantum chemistry. That is the real part. And after I get this, I will get an energy, the ground state energy, which will depend on the position of the nuclei. Now, with this energy, I can then later worry about the motion of the nuclei. Because if the nuclei lower the energy by getting closer, obviously this will induce a motion of the nucleus to get a more favorable energetic configuration. Okay, so that's what we have done here. First, we have solved the Schrodinger equation for the electron. That's the wave function of the electrons that depends on the nuclei only parametrically. This is the potential energy where the Q are static. How do I know? There is no derivative with respect to Q here. And this is the energy that depends on the position Q parametrically. That's the electronic problem. After I solve the electronic problem, I can worry about the dynamic of nuclei. In this rigorous treatment, I'll worry about the second Schrodinger equation that concerns the dynamics of nuclei. However, I want to say I should use a different symbol here because this is the potential energy that I calculated. This is the so-called Born-Oppenheimer energy surface. And it is not really a potential energy. It is the ground state energy of the electronic problem at fixed nuclear position, which of course is the energy of the system at fixed nuclear position. That's why it is interpreted as a potential energy for the nuclei. And this is the energy of the system after I solve the Schrodinger equation. Now, I need to solve the Schrodinger equation if my nuclei behave quantum mechanically if they are delocalized. But for most application we are interested in, we don't need to do that. We do not need to do that because nuclear, we discussed this at the beginning of this course, for many practical purposes at room temperature, for all the practical purposes basically that are concerned with biomolecules, they can be treated as classical objects. So rather than solving the Schrödinger equation, we can solve Newton's equation for the nuclei with a force taken for the gradient of the Born-Oppenheimer energy. So although the complication, in spite of the complication of this lecture, which I included for your reference, all I want you to really grasp and really understand and really retain in your background is the following statement I'm going to make now. So whatever I've said so far, if you want, is because I think as a lecturer, I cannot be too much unwavering. I have to show you how things emerge from a calculation. But what I really want you to know is what I'm going to tell you now, which summarizes everything on more physical basis. I have a complicated problem which involves electrons and nuclei. And due to the adiabatic approximation, I split it into two problems. First, I solve for the Schrödinger equation for the electrons at fixed nuclear position. So first I solve the electronic problem and I look for the ground state energy only. This will give me the potential energy of electrons if the nuclears are held fixed. How does this equation know that the nuclei are held fixed? There's nothing that involves derivatives with respect to nuclear positions. And after I've done this, I can solve for the dynamic of the nucleon. For instance, by solving Newton's equation for the nuclei, which corresponds to making a classical approximation. Sorry, I should have used the Q notation for the nuclei. I apologize, in the previous slides, I should have used okay, I have a problem with notation. The energy, of course, depends on the nuclear coordinate. Let's see if I've done, yes, I've done that correctly before. And of course, here, that was the mistake. Here, these are nuclear position. Okay, fine. I finally made it. So, this is the foundation of anything you will be doing in the rest of this course and in the next course on molecular simulation. That's how computational chemistry is done, at least conceptually, for macromolecules. You have to find the energy corresponding, coming from the electrons of a systems with fixed nuclear position, and then differentiate with, take the gradient of this energy, this ground state energy will give you the effective force experienced by the nuclei if they're considered as classical particles. So the motion of the nuclei will be determined by the motion of the electron, by the forces induced by the electron. And I want to give you an example. Okay, in this video, you will see a calculation that my lab was involved with. Any lab has done other kind of calculation. There's nothing, I don't want to emphasize what scientific contribution of my group has done, but rather on the class of problems that people like people in my lab are actually dealing with. And you see, this is, for instance, the problem of misfolding of a particle called prion protein, human prion protein, into a toxic aggregates called prions that are responsible for neurodegenerative disease. Now, what you see there is, of course, the stripes here. They represent the backbone atoms of a protein, and these are proteins misfolded into these sort of barrels. And what you see is a simulations of how this process is actually happening. Now, clearly, in order to perform this simulation and gain insights that is useful for biology and molecular biology, and possibly in the future for therapy, all you really care is the motion of the heavy particle, the atomic nuclei. But you know about the motion to be able to determine even classically the motion of the heavy nuclei. What you need to do is to solve Schrödinger equations for many different nuclear configurations, probably then finding an approximate formula, analytical formula that accounts for all this information. So really, chemistry, molecular mechanics is the result of following the motion of the heavy nuclei, even classically, under effect of an effective potential produced by the ground state energy of the electrons. That's the scheme. And this scheme was worth the Nobel Prize for Chemistry. I think it was 2013. So understanding that you can basically do molecular simulations this way and learn about molecular mechanics by making this very well clear, theoretically sounded separation and theoretical scheme was the beginning of application of computer simulations to biology. And you can only imagine how much implication this is beginning to produce in science. And from the point of view of quantum mechanics, what it really amounts to, going back to our problem here, what it really amounts to is to be solving what it really amounts is to be solving this problem here. So in the rest of the course, we will be doing with part one of this problem. This is the quantum chemistry problem. And we will be dealing on getting this potential energy. Next year, Lattanzi, Professor Lattanzi and Professor Tubiana will take over, use this or approximations of that to determine these forces that is called the force fields. Sometimes you can use quantum mechanical calculations. Sometimes quantum mechanical calculations are not quite as accurate as we want, and you have to sort of use a semi-empirical or completely empirical approach. Well, you'll learn about all the details next year. And we'll apply to nuclei to predict the motion. And this will be a complicated classical problem with a lot of additional nuances and theory associated with it. And this will be the task of next year course on molecular simulations. But it is important that we bridge the gap from fundamental physics to this ingredient here. So in the rest of this course and in the final exercise, you will be solving the electronic problem. Okay. Next lecture will be how do we solve the electronic problem? And I think I'm owing you 2 more lectures plus probably 3 more lectures in which basically we tackle this problem and we develop suitable approximation for this problem. And also we try to do an analytic calculations to see that in fact by doing this you can predict the existence of molecules, and we will focus on the simplest possible molecule, the hydrogen molecule, and learn that with the machinery, mathematical machinery and with this Born-Oppenheimer approximation, you can in fact predict the existence of molecules and possibly predict extraction. Okay, it's getting exciting here. I hope you're following up with excitement, even if it's a bit difficult to follow. We'll see you next time.